To calculate voltage drop for an underground service, you can use the formula percentage voltage drop equals 2 times the length times the current times K divided by the voltage. The ambient temperature is a crucial factor. In this case, 30 degrees Celsius is used. The temperature correction factor K is 0.93. The length L is 250 feet, which converts to 76.2 meters. The connected load I is 154 amps, and the voltage E is 240 volts. Plugging these values into the formula, the percentage voltage drop equals 2 times 76.2 times 154 times 0.93, all divided by 240 times 240, which equals 3.1%. Therefore, a 3.1% voltage drop is correct. To calculate the conductor size, you can use the circular mil formula. The formula is circular mils equals length times current times the efficiency factor divided by K times the voltage drop times the voltage. The load current I is 154 amps. The efficiency factor is 95% or 0.95. The voltage drop is 3% or 0.3. The voltage E is 240 volts. Plugging these values into the circular mil formula, circular mils equals 76.2 times 154 times 0.95 divided by 0.93 times 0.3 times 240, which equals 226,722 circular mils. Using a conductor table for a voltage drop of 3% at 154 amps, the recommended conductor size is 250 mcm aluminum. In conclusion, the voltage drop calculation of 3.1% is correct. A conductor size calculation using both methods, the circular mil formula and the conductor table, suggests using 250 mcm aluminum. Therefore, the correct answers are a voltage drop of 3.1% and a conductor size of 250 mcm aluminum. When performing voltage drop calculations, several key factors must be considered to ensure accuracy and compliance with electrical codes. Firstly, the ambient temperature significantly impacts the conductor's resistance. Higher temperatures increase resistance, leading to a greater voltage drop. The temperature correction factor, K, adjusts for this effect and varies depending on the conductor material and insulation type. Secondly, the length of the conductor directly affects the voltage drop. Longer conductors result in a more significant voltage drop due to the increased resistance over the distance. Accurate measurement of the conductor length is crucial for precise calculations. Thirdly, the connected load, measured in amps, determines the amount of current flowing through the conductor. High current loads cause a greater voltage drop. It's essential to consider the maximum expected load when sizing conductors to prevent excessive voltage drop under peak demand. Fourthly, the voltage level of the system influences the voltage drop. Lower voltage systems are more susceptible to voltage drop issues compared to higher voltage systems. Maintaining the voltage within acceptable limits is critical for the proper operation of electrical equipment. When using the circular mil formula to calculate conductor size, several additional factors should be taken into account. The efficiency factor represents the percentage of power delivered to the load. It accounts for losses in the system such as transformer losses and other inefficiencies. Using an appropriate efficiency factor ensures that the calculated conductor size is adequate to deliver the required power. The voltage drop percentage specifies the maximum allowable voltage drop in the system. This value is typically specified by electrical codes and standards to ensure that equipment operates within its rated voltage range. Selecting an appropriate voltage drop percentage is essential for maintaining system performance and reliability. Conductor tables provide pre-calculated conductor sizes based on various factors such as current carrying capacity, voltage drop, and conductor material. These tables simplify the conductor sizing process and ensure compliance with electrical codes. However, it's crucial to use conductor tables that are relevant to the specific installation and to consider any unique conditions that may affect the conductor's performance. When selecting conductors for underground services, several additional considerations should be addressed. Firstly, the type of soil surrounding the conductor affects its heat dissipation. Different soil types have different thermal conductivities, which influence the conductor's temperature. It's essential to consider the soil conditions when determining the appropriate conductor size. Secondly, the depth of burial affects the conductor's temperature. Deeper burial depths result in lower temperatures, which can improve the conductor's current carrying capacity. However, deeper burial depths also increase the cost of installation. Thirdly, the presence of other underground utilities can affect the conductor's temperature. Heat generated by other utilities can increase the conductor's temperature, reducing its current carrying capacity. It's essential to coordinate with other utility providers to ensure that the conductors are properly sized and spaced to prevent overheating. In summary, accurate voltage drop and conductor sizing calculations are essential for ensuring the safe and reliable operation of electrical systems. By considering all relevant factors such as ambient temperature, conductor length, connected load, voltage level, efficiency factor, voltage drop percentage, soil conditions, burial depth, and the presence of other utilities, electrical professionals can select the appropriate conductors and ensure that the system meets all applicable codes and standards. Let's delve deeper into each of these factors to provide a more comprehensive understanding. Firstly, ambient temperature plays a critical role in determining the conductor's ampacity. The ampacity of a conductor is the maximum amount of current it can carry continuously without exceeding its temperature rating. Higher ambient temperatures reduce the conductor's ability to dissipate heat, thereby lowering its ampacity. Electrical codes, such as the National Electrical Code, provide ampacity tables that list the allowable current carrying capacity of conductors based on their size, insulation type, and ambient temperature. It's essential to consult these tables to ensure that the selected conductor has sufficient ampacity for the expected load. Secondly, the length of the conductor directly impacts the voltage drop. As current flows through a conductor, it experiences a voltage drop due to the conductor's resistance. The longer the conductor, the greater the resistance and the larger the voltage drop. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Electrical codes typically limit the allowable voltage drop to a certain percentage of the source voltage, such as 3% for branch circuits and 5% for feeders. Thirdly, the connected load determines the amount of current that the conductor must carry. It is essential to accurately calculate the connected load to ensure that the conductor is properly sized. The connected load includes all of the electrical equipment that will be connected to the circuit, such as lights, appliances, and motors. Electrical codes provide guidelines for calculating the connected load based on the type of equipment and its power consumption. Fourthly, the voltage level of the system affects the voltage drop. Lower voltage systems are more susceptible to voltage drop issues compared to higher voltage systems. This is because the same amount of power is delivered at a lower voltage requires a higher current, which results in a greater voltage drop. When designing electrical systems, it's important to consider the voltage level and to select conductors that are appropriately sized to minimize voltage drop. When using the circular mill formula, the efficiency factor accounts for losses in the system. These losses can include transformer losses, conductor losses, and other inefficiencies. The efficiency factor is typically expressed as a percentage and represents the ratio of power delivered to the load to the power supplied to the system. Using an appropriate efficiency factor ensures that the calculated conductor size is adequate to deliver the required power. The voltage drop percentage specifies the maximum allowable voltage drop in the system. This value is typically specified by electrical codes and standards to ensure that equipment operates within its rated voltage range. Selecting an appropriate voltage drop percentage is essential for maintaining system performance and reliability. Conductor tables provide pre-calculated conductor sizes based on various factors, such as current carrying capacity, voltage drop, and conductor material. These tables simplify the conductor sizing process and ensure compliance with electrical codes. However, it's crucial to use conductor tables that are relevant to the specific installation and to consider any unique conditions that may affect the conductor's performance. For example, If the conductor is installed in a conduit or raceway, its ampacity may be reduced due to the limited ability to dissipate heat. When selecting conductors for underground services, several additional considerations should be addressed. The type of soil surrounding the conductor affects its heat dissipation. Different soil types have different thermal conductivities, which influence the conductor's temperature. Sandy soils, for example, have lower thermal conductivities than clay soils, which means that they are less effective at dissipating heat. It's essential to consider the soil conditions when determining the appropriate conductor size. The depth of burial affects the conductor's temperature. Deeper burial depths result in lower temperatures, which can improve the conductor's current carrying capacity. This is because the earth acts as an insulator, protecting the conductor from temperature fluctuations. However, deeper burial depths also increase the cost of installation. The presence of other underground utilities can affect the conductor's temperature. Heat generated by other utilities, such as gas pipelines or steam lines, can increase the conductor's temperature, reducing its current carrying capacity. It's essential to coordinate with other utility providers to ensure that the conductors are properly sized and spaced to prevent overheating. In addition to these factors, it's also important to consider the type of insulation used on the conductor. Different insulation types have different temperature ratings, which affect the conductor's ampacity. It's essential to select an insulation type that is appropriate for the expected operating temperature of the conductor. Furthermore, the installation method can also affect the conductor's ampacity. Conductors that are installed in free air have a higher ampacity than conductors that are installed in a conduit or raceway. This is because conductors in free air are better able to dissipate heat. Finally, it's important to consider the future needs of the electrical system. If there is a possibility that the load will increase in the future, it's wise to select conductors that are sized to accommodate the increased load. This will prevent the need to replace the conductors at a later date, which can be costly and disruptive. By carefully considering all of these factors, electrical professionals can ensure that the conductors are properly sized and installed to provide safe and reliable electrical service. The goal is to minimize voltage drop, prevent overheating, and comply with all applicable codes and standards. Remember to consult the latest edition of the National Electrical Code and other relevant standards for the most up-to-date information and requirements. Proper conductor sizing and installation are essential for ensuring the safety and efficiency of electrical systems. Let's delve deeper into the practical aspects of calculating voltage drop and conductor size, providing a step-by-step guide that incorporates real-world considerations. Firstly, gather all necessary information. This includes the connected load in amps, the length of the conductor run in feet or meters, the voltage of the system, the ambient temperature, and the desired voltage drop percentage. Accurately determining the connected load is crucial. Refer to the nameplates of all electrical equipment that will be connected to the circuit and sum their current requirements. For motors, use the full load amps listed in the nameplate. For lighting, calculate the total wattage and divide by the voltage to obtain the current. Secondly, determine the appropriate temperature correction factor. Consult the NEC tables to find the temperature correction factor based on the ambient temperature and the conductor's insulation type. If the ambient temperature is higher than the temperature rating of the conductor, you'll need to direct the conductor's ampacity accordingly. Thirdly, calculate the voltage drop using the appropriate formula. For single-phase circuits, the voltage drop formula is voltage drop equals 2 times the length times the current times the resistance per unit length. The resistance per unit length can be obtained from NEC tables or from conductor manufacturers. For three-phase circuits, the voltage drop formula is voltage drop equals the square root of 3 times the length times the current times the resistance per unit length. Fourthly, compare the calculated voltage drop to the allowable voltage drop percentage. If the calculated voltage drop exceeds the allowable voltage drop, you'll need to increase the conductor size or reduce the length of the conductor run. Fifthly, calculate the required conductor size using the circular mil formula or conductor tables. The circular mil formula is circular mils equals 2 times K times the length times the current divided by the allowable voltage drop. K is a constant that depends on the conductor material. For copper, K is approximately 12.9. For aluminum, K is approximately 21.2. Alternatively, you can use conductor tables to select the appropriate conductor size based on the current carrying capacity and the allowable voltage drop. Sixthly, select the appropriate conductor insulation type. The insulation type should be suitable for the operating temperature and environmental conditions. Refer to NEC tables for guidance on selecting the appropriate insulation type. Seventhly, consider any dirting factors that may apply. If the conductor is installed in a conduit or raceway with other conductors, you'll need to dirt its ampacity according to NEC tables. Eighthly, verify that the selected conductor size is sufficient to carry the connected load and meet the allowable voltage drop requirements. Use NEC tables to confirm the conductor's ampacity and voltage drop characteristics. Ninthly, document all calculations and assumptions. This documentation will be helpful for future reference and for demonstrating compliance with electrical codes. Tenthly, consult with a qualified electrical engineer or inspector to review your calculations and ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. We remember that electrical work can be dangerous. Always follow safe work practices and take appropriate precautions to protect yourself from electrical shock and other hazards. By following these steps and paying close attention to detail, you can ensure that the electrical system is properly designed and installed to provide safe, reliable, and efficient service. Now, let's consider some real-world examples to illustrate these concepts. Firstly, imagine you're designing an electrical circuit for a residential kitchen. The circuit will supply power to a refrigerator, a microwave oven, and several small appliances. The total connected load is 20 amps. The length of the conductor run is 50 feet. The voltage is 120 volts. The ambient temperature is 30 degrees Celsius. The allowable voltage drop is 3%. Using the steps outlined above, you can calculate the required conductor size and select the appropriate insulation type. Secondly, suppose you are designing an electrical feeder for a commercial building. The feeder will supply power to several branch circuits that serve lighting, receptacles, and HVAC equipment. The total connected load is 150 amps. The length of the conductor run is 200 feet. The voltage is 208 volts. The ambient temperature is 40 degrees Celsius. The allowable voltage drop is 5%. Again, following the steps above, you can calculate the required conductor size and select the appropriate insulation type. Thirdly, consider an underground service for a new home. The connected load is 154 amps, as in the original problem. The length is 250 feet. The voltage is 240 volts. Using a 30 degrees Celsius ambient temperature in aluminum conductors, you would follow the same steps to confirm the 250 mcm conductor size. These examples illustrate the importance of carefully considering all relevant factors when designing electrical systems. By accurately calculating the connected load, determining the appropriate temperature correction factor, calculating the voltage drop, and selecting the appropriate conductor size and insulation type, you can ensure that the electrical system is safe, reliable, and efficient. Remember to consult the latest edition of the National Electrical Code and other relevant standards for the most up-to-date information and requirements. Proper electrical design and installation are essential for protecting people and property from electrical hazards.